this was a good 3 years, and as it turns out, the official opening was today, and we had no less than Mr. Michael Bloomberg, the philanthropist, present for an hour. Pat Kenny interviewed him, and it was an extraordinary position to be in, to see somebody that powerful be and just give their thoughts on life. Really, that's really what it was all about. But so it coincided with the opening of the building. But here we go with the famous V columns at the front of the building, which we'll get to in the talk. Just what we're going to talk about. So the project introduction, the site, client brief, and the challenges really, the site history. Before we really broke ground at all, we did a due diligence on the project for over a year. So it was over a year's work before we kind of did any kind of any digging at all. The scheme development and the construction sequences and challenges. Okay. So project location right in the heart of the city. St. Stephen's Green, Grafton Street at the top left, and this is as you can see, the red box here, just tied up against York Street, a 5-story, 6-story apartment over basement, immediately to the west of us. Existing car parking to the south, and a lane to the east of us as well. So right in the heart of the city, with residents in this block here, which were a challenge. Team, I suppose the client, RCSI, architect Henry J. Lyons, ourselves on the civil structural. Bennett's had the real fun of making this happen on the ground, and in conjunction with the basement temporary works, which would have been done by Byrne Newby. Project client. Really, it's all about the client in this particular project, because when would you ever stick a sports hall 4 stories down in the middle of the city? I suppose you do it really when you're the Royal College of Surgeons, and you have a heritage, and you have they've been there since really the 1810 is when this building opened. And they're one of the few kind of, obviously Trinity or city bound, but in terms of other education facilities, they've decided to stick in the city centre. And in fact, they have facilities around Dublin and Beaumont and a few other locations, and they're actually being relocated into the facilities here. And really the fact that they're wedded to this part of the city, they need space. There's planning constraints in terms of a set parapet height that defines the streetscape, which in this case is a 4-story building. They wanted a schedule of accommodation which would be over 10 stories. So there was only one option, and that was to go down. Okay. So they started doing that around the mid-noughties, 2005, 2006, and they got this basement box constructed. And then things went south. The contractor was McNamara's, they went bust. The architectural firm went bust, and the project stopped. And it stopped for 3 or 4 years, and they got a new design team, which was Henry J. Lyons Architects. We interviewed for the project and managed to get on, and so we had a challenge of a site which was inheriting a box, essentially. So we inherited this box, and that's really the starting point. But really, if it wasn't for the college, this kind of building doesn't happen. But their dedication to the area and the heritage of their commitment to the local area is what made it happen. So this is when you walked inside, and it was pretty daunting. These things you become immune to after a certain number of years working on the project. But when you first, there was a stairwell. There was a scaffolding stairwell down, which would have exceeded its temporary design life. This is really what we inherited: concrete box, about 16 meters deep, 16.5 meters deep, 21 meters wide. It had the remnants of temporary works still in place, so you can see that there's internal steel props. There's also at the top there's external anchoring. the anchoring at the lower level would have been de-stressed and replaced with the internal steel props. So that's really what we inherited. At the back of the building there was a single-storey car park. Ground conditions typically filled for a story height with gravels to essentially half the depth of the box, and the other half of the box was limestone rock. So I have to mention it. There's Paul Healy. That's for scale. There's Paul Healy. Yeah, I know you know him, so you can get an idea of scale. And if you're still troubling with the scale, I did search hard for a Dublin bus elevation, and I couldn't get one. So this is what I did instead, to try and give an understanding of the scale. And I suppose one of the best things early days was drawing the kind of cross sections as best we could in terms of developing well, what are the constraints. So this type of information has to be derived from SI, topographical surveys, record drawings, and some further investigations. But developing good cross sections across the site is fundamental to understanding what are the constraints and how are they going to affect how we go about this project. But you can see the cross section and the long section here. And on the long section, just to give you again for scale, the apartment block that you saw at the start is literally sitting, touching the basement box here. Before they constructed the apartment block, they had coordinated at the time that the deep dig was going to happen. So they had piled down to approximately formation level, a bit below it, in anticipation of the box happening. And that's really how they managed a lot of the support facilities on that side. You can see here, in fact, that the reverse, what you normally expect to see on the corner of the basement, and apparently that was related to piles not going down firmly originally. So, just to decline brief. So this was the original box, and they said, okay, the box isn't big enough. Okay, we need more space. So that was what everybody didn't want to hear. What they wanted was clinical simulation training, surgical training, and that's over 3 floors, which we had the joys of looking at today, simulating the labour wards, which was and surgery wards. They wanted a library over 3 floors, 540-seater auditorium, all stacked then on top of the multi-storey, multi-purpose sports hall. Just to give some plan, this was the existing, and the yellows, the kind of bit that they want to extend out. So in cross section you can see the kind of scale of the dig that they wanted to extend this basement by. Just over 11,000 square metres of accommodation. And this is how it kind of distilled in terms of the architectural planning. So in summary, really, the challenges were the obvious thing of making a box bigger, okay, a basement box. Nobody's going to thank us for putting the column in the sports hall or the auditorium, so this has to be column free. So we have to bridge over that space. There's the planning restrictions on the building height, so essentially there's a parapet streetscape that's been defined for the past so many years. And from a planning point of view, that dictates what the planners want to see here and here in terms of extended site lines. So 10 stories with 4 stories below ground. And of course in these upper laboratory and clinical simulation suites, there was strict vibration requirements in terms of floor accelerations. With a building like this, it's a small footprint, it's 40 by 30, but it's heavily serviced, heavily serviced. There's a lot of services going on. And big spaces need big ducts, okay? Putting buildings below ground, smoke extract and fire becomes a big challenge. So extensive mechanical and electrical servicing, and so when they configured the building originally, there was to be double height spaces in there, but there were a lot. You can see here this side has got intermediate floor plates propping this wall. So the walls were generally 350 where they were propped, 500 where they were to be double height, and a metre thick slab. And I said, well, we'd actually like to move the sports hall from this end of the building to this end of the building. So we had a double story high, 350 mil wall to figure out, which we did. So there is I suppose, the real brief and the challenges, okay? So it was the east wall strengthening to accommodate the alteration from single story high to double story high. So due diligence in the site history. There was tenement housing here historically, and would you believe it, in the 30s, they built replica tenement housing and just put the same thing back in. And it's only actually in doing some preparation for this that I found that when they demolished the building, an artist actually did a study of some of the features in the housing, such as the fireplaces, and this is actually a key holder for all the keys of the apartments, and somebody made art out of it, which is, you know, admirable, I think. But nothing unusual on the site history, other than so in terms of nasties in the ground and all that kind of stuff, it was all pretty clean. A couple of leg bones maybe from across the road. You can see we're all clean. Really, the bulk of the site had been developed by the time we got there with the construction of the original box. But only to say that the original building would have had a basement level. And you find in Dublin in particular that the setting of original basement level would really define, would generally be above groundwater levels. So it's an important indicator of, in the past, the sector floor levels typically above groundwater. Okay, but pretty benign in terms of site history, but residential use essentially. So this is, and to be fair to the original design team, they were good enough to meet us, okay? And we got access to photographs, design drawings, not much photographs though, but we had design drawings, we had GA drawings, we had RC drawings, but these photographs tell it all, and I suppose if you want a site investigation, borehole, this is as big as they come, okay? So essentially, what they did at the time, you got to remember, it was mid to late noughties, and the market was aggressive, and it did things in a pretty kind of aggressive way in terms of cost, program, and so on. So they decided, when they constructed this originally, the seeking pile only be overburden. So the top half of the site was seeking pile for the perimeter. On plan then, what they had is Odex piling, which would come foot height and down to maybe 2 meters below formation, which would take out the vertical component of the anchors. So if you had all of these piles, as you can see in here, just the piles all sitting at the rock level. And if you didn't anchor that, there's a chance that they'll slip. So they took out the vertical component of that reaction with the steel piles that went full height. So the seeking pile, male, female, with the Odex, and then essentially the dig happened in stages. So they would, once the piling was complete, they would anchor with steel whalers in this case. They had steel whalers and ground anchors when we could do them easily. It's getting harder now in Dublin with the roads division. I'm not sure in the rest of the country, but certainly we're having to kind of go towards more glass fibre rods these days and so on. So they're the traditional 76 with steel anchors. So you have your pile, whaler, your anchors. Once that's propped, you go down in stages and so on. Ground conditions, as I said, the water table, just to give you an idea of the water table, it's about 3 meters below, just a little bit below the floor level of the tenement housing. And actually this gives you a bit of an insight into different ways to crack on a problem. So the original designers, you can see, if you look closely, there's 2 lines of columns here, and there's castellated steel beams, one over the width of the box. So that was their approach, the original designer's approach to bridging the span. We wanted to do something a bit different when we got to that part of the problem. The other thing you'll see, of course, is the anchor flotation anchors to stop this thing popping up. So that's what we inherited. Again, we still haven't designed a building here. We've got a brief and we've got a site and we're still learning all the time. And as part of that, we have to do due diligence in terms of what they built. Is it strong enough? What were the standards? What's the condition? What was the concrete like? So we had to model the features that we could identify, carry out a full suite of material testing, and I suppose you can see a clue to some of the kind of challenges that they had. Okay, groundwater coming through the green concrete as it happened. So let's go back to that slide. And they did kind of nominal sheet, they did nominal treatment. You can see maybe here, so you have, in terms of the rock, you can see kind of, that's the open rock face there. And here you can see it's got the shotcrete on it. So what that meant is that when they were coming back up the basement, they would have put bentonite membrane on the wall in terms of waterproof and protection. But when they were coming back up, they had limited the means of controlling groundwater, and that caused problems. So the original construction methodology caused problems for the green concrete essentially, and there was a legacy of that. That was really the outcome of the, and that took a long time to get to that stage, and we're still, now we got to cut it open and do some surgery, some real surgery on it. The last thing I'll say in terms of the due diligence, we spoke about the anchors. So naturally, when you get a box that size and you shove it into the ground, you're engaging all the groundwater, and you've got hydrostatic forces to resist. Couple that then with the fact that the sports hall is over 18 metres, 12 metres of water pressure. So you can imagine 120 kilonewtons per square metre coming up on a metre thick slab. It ain't going to be good. So they were passive anchors, and we thankfully had the test results. So they would have carried out one proving test and 4 acceptance tests. Okay, and really the outcome of that was that we were able, initially when we looked at the anchors, we felt that they were struggling in certain areas. If you just got a floor area, multiplied it by the uplift pressure, took away the dead weight of the metre thick slab, it was exceeding the capacity of the anchors. So we had to go through a routine program of using the upper and lower bound stiffnesses that the anchors gave us from the site testing. So we had anchor deflections of between 5 and 10 mil essentially. And when you model the stiffness of an anchor, I mean, they had no overburden, they were straight into rock, but yet there is a bit of a stiffness associated with it. So when you put them at safe working load, give them a stiffness, don't give them an infinite stiffness, give them the stiffness of 5 mil under safe working load. And what started to happen was it started to redistribute the loadings from an anchor that otherwise would have been overstressed. So that was an important point in terms of getting that over the line. The anchors were about a 5 metre grid, 7 metre embedment, and that was based on the bar grout interface. Some of the details are there in terms of the 63.5 mil Dividec bar, which was a Dividec plus, 1360 kilonewton safe working load, so plenty going on there. So they're needed permanently. The building is probably they're needed permanently in terms of uplift as well as the slab. So in most cases you might only have it for the slab only, but because we're down so far with 12 metres of water pressure, they're needed in both scenarios. So just to recap in terms of the due diligence, no issues with the concrete composition, by the way. The concrete that we used inside was fine, but it was the methodology that was their downfall. Okay. And they had 9 months of crack injection to sort that out. Probably no need to go through the site investigation, you saw the borehole, but before we had, somebody had left a little legacy, I'm not sure if it would be a garden bench or what. It's a fine grain rock that's there, okay? The argillaceous rock, it's really a fine grain limestone. And in this site, you can see the kind of fracture spacing, 3, 4, 500 mil. And if anybody knows the interchange in Lucan, you can see the beds of the limestone kind of folding and undulating like waves. But in this case, and it was an important consideration for us, it was essentially fractured horizontally across the site. You can see that back in the, look how horizontal the bedding is in these. That was an important point, because when we come to it later, we needed to figure out how much of this rock are we going to take onto the building as a lateral pressure. And depending on the inclination of the rock failure planes, or bedding joints, that dictates that number. So the more horizontal that is, the more stable that is as a mass. And that's it here. I mean, we do a lot of work with this with AGL, to refer to them, in terms of deriving for the Eurocode design approach 1 and 2, for your design 5 values, for your load combinations and your material combinations, and you can see essentially the different, for the different design approaches, design approach 1 or 2, we had the active pressures of 0.26, 0.19, 0.22 for the lower, for the higher load factor, and for the lower load factor, they get increased. And in terms of the rock, we have a value of 0.07. So long term, it's probably best practice to allow for the pressures from the rock, and the more inclined that the rock bedding joint is, the more you should probably pay. In terms of the, I suppose before the job started, I was a bit I was more than curious, even though they had done this before, how hard is it going to get rid of this 8 meters of rock? And in terms of the excavatability index, it's in the kind of medium to strong zone. Essentially it gets ripped out with a little bit of rock breaking. The fact that it's fine grained, you have that horizontal bedding, the lumps are not that big. There was a bit of rock breaking, but we managed it in the heart of the city, and it's 8 meters. In terms of bearing pressure, it's medium to strong. Safe bearing pressure of 2,000 kilonewtons per square metre. The water pressure, as I said, was essentially 12 metres of water pressure on this, 120 kilonewtons per square metre, and we set the water table to approximately just underside the historic tenement housing level. In addition to that, at the back of the building was car park access, which was at grade. So we knew with confidence that this doesn't go right up to street level, which if you read some of the Eurocodes, they're asking you to do, but it's the worst credible level is what you go to, okay? So what was the waterproofing strategy? So we have a lot of water to keep out. You have to go through a process of explaining to the client what's wet and what's dry. It's not black and white, and BS8 102 2009, when they changed it, went from a more prescriptive approach to being more risk-based, and it is 50 shades of blue. Okay, there isn't a tipping point with this thing. But you can see, you can get, these are the old definitions before they changed them, but it gives you a good idea in terms of, even when we are up at the very top of grade 3 and grade 4, moisture is still coming through the walls, okay? So, grade 1 would be your basic car park and so on. But in the BS8 102 2009, if your groundwater is above basement level permanently, they say it's high risk, okay? So when it is high risk, the suggested approach is combined protection. So there's 3 general different approaches, type A, B, and C. So A is barriers, that's a membrane of some sorts. B is structural integral, so it's the crack widths and designing a rebar to be the centres and the size to control the crack widths. And type C is your drain protection. So The 0.2 mil crack width is what you would have used historically. When the Eurocodes came along, that changed, so you had to calculate the crack widths. And it's done on the basis of the height of water across the width of the wall. It's a kind of a head relationship across the width of the wall. And for a basement that deep, I don't know what the crack widths would have been, but they were just tiny, and you couldn't design for them. The original basement box had a design crack width of 0.3 mil, so we stuck with that. Okay. So the chosen solution was barrier type A and type C. That's how that was the waterproofing strategy. To give us essentially grade 3, we needed grade 3 in terms of the whole space is an occupied space, bar one water tank room, which is actually at level -5. Regardless of what your strategy is, you definitely need good concrete, okay? And the big issue in terms of, the big issue with that, I suppose, is the water cement ratio. Water cement ratio and controlling cracking. And controlling cracking is really reducing the heat that's in the slab, so it's the mix, so using the GGBS and so on. But the biggest thing would probably be water cement ratio. Just to give you a feeling, okay, these are all of the areas that you can be attacked from. It's really through the slabs, the walls, and by the way, as you'll see in a moment, this definitely happens in the rock in Dublin, where you create, this could be a seeping pile. You think you're cutting off the water supply, but it comes up, okay? But in terms of the concrete mix, this is water cement ratio 0.6. The yellow are the kind of the capillaries or the voids that you're going to have. And concrete only needs a water cement ratio maybe around 0.25 to actually cure, okay? It's somewhere between 0.25. You're never going to get a clear answer on that one. It varies between 0.25 and 0.3. But whatever it needs, it's around that number. And anything that's left is only idle. And it's only there to acclimate it. Its job is done. So it just exits and it leaves voids behind it, okay? So that's why you can see with the water cement ratio 0.6 and this is 0.45, which is what we'd be using. The guys will tell you that they're down to 0.4, but the further you go down, you get workability issues and you can have problems associated with that. But key issue, water cement ratio, and we use 70% GGBS mix as well, by the way, in terms of reducing the heat. The waterproofing, so we use the bentonite membrane. I'd say predominantly because the existing box had it, so we were going to tie in whatever they used. And a big thing with it is, you would have seen a couple of years ago that they would have just break down to a seeping pile profile, which is not recommended really. You really have to shotcrete whatever face you're going to fix. You need a good sound, pretty even surface. But that's the bentonite membrane system. This is where the anchors penetrate. Anytime these anchors penetrated the slab, there were weaknesses, so there was obviously a lot of tension then. But this is really, so we had a box, and we had to cut a piece off it and stick a new piece on. And making a box bigger, what that joint would be, was done with an injectable tube system. We used a mixture of stuff with grouts, resins, gels. By and large, it worked very well, particularly on the slab actually, which was 1 metre thick. But that was a key part of when you're joining two concrete components underground. The normal external water bar or internal hydrophilic strip, they need to be done really well, and they need sound, particularly the water bar between two surfaces. That surface has to be almost like this. If there's any deviations on that, they become weak. So with these are re-injectable, and you have different levels of material that will accept a first go and a second go and a third go, and you keep at it. So you inject, every time you inject, you wash out the tube afterwards. So the tube is a run from socket to socket, stays free. That has to be clear at all times. So you wash that out. with water between after each process. And the tubes are arranged with perforations that will essentially allow stuff to get out but not get in. Okay. There's a couple of different suppliers of that system. And I'd say the more we had one problem actually we had with this was we had grouts, what they could say, flashes, and it went off. Didn't get to where it needed to, and we ended up having to crack inject in some local areas as a result. But by and large, the system worked fairly well, and we've just done it in the passport office. Not this particular brand, and it's worked quite well again actually. So I'm becoming a fan. Right, scheme development. So with long span. 10 stories. Back of house. Building is kind of split in two halves in terms of usage. There's the front of house and the back of house. Back of house is all support facilities. All the upper levels is offices, plant, showers, all that kind of stuff. And front of house is the business part of the building. Sports hall, auditorium, library, and clinical teaching. So when we first looked at it, I suppose you're automatically thinking of steel, you know. In fact, it's the reason we got the job. When we interviewed for that, their early days, they had the 40 metres just trussed with a column either side of the building. We had done that, or something like that, at the convention centre, and it was one of the reasons we got the job. But in fairness to the architects, they really worked with us in developing the scheme, and eventually we got a grid of columns of 4.6 metres into the. But in terms of the concrete scheme, the steel option, this was a kind of a 9 by 9.5 grid, that kind of thing. Wanted to be flat slab. The box wanted to be concrete. So we originally looked at steel constant beams for the auditorium, same for the ground floor, and we looked at cell beams for the individual floors. So that was the starting point really. But there was a bit of a cost issue with steel. So the problem with steel is fire protection. And that was the first issue. And the second issue was service distribution. So you can see here with the cell beams, I spoke earlier about the spaces. As the project developed, the need for horizontal distribution in the floor plates became greater. And as wonderful as the cell beams are, it just didn't work with it. And it's not going to cell beam out. So between service distribution, costs in relation to fire protection, cell beam or long span steel was getting the kicking. And then in conjunction with that, they'd done an amount of peer reviewing buildings all over Europe and in the States actually of buildings. And the more they looked at them, the more they liked the idea of expressing the material in the building. Okay. Just a small slide in Funicular Structures. So Mr. Robert Hook here, as hangs the cable, so what inverted is the arch. Okay? That's what this building is about structurally in terms of the superstructure. We wanted to in fact, I won't say instructed, but everybody wanted to look at concrete, see how can we make a concrete solution span 18 metres plus over a sports hall and over an auditorium. So we looked at the transfer. So this is the basic kind of funicular structure. So what is it? It's the shape that a cable will take, okay? Cables are really brainy because they'll only do what they have to do. And they'll always take up the shape that they need to do. So you can see here, we're giving cable arrangement, cable load. It assumes the shape, it assumes the most appropriate shape to take in terms of least work, okay? It can only take axial tensile forces. So it changes its shape. It's a clever little dicky. It changes its shape to reflect the loading that's on the load system, okay? And that's the best way to visualize it really, in terms of single load in the shape, and 2-point loads in the shape, and 3-point loads in the shape. And when you invert them, that's the most efficient structural shape to get, okay? Anybody's familiar with the Sagrada Familia, the Mad Cathedral in Barcelona, the way the shape is divided was in relation to hanging all the weights to mimic the axial load as a tensile load. And these are actually samples of the experiments that were run to get the shape of this cathedral, and then flip that shape upside down, and that's what you want to be at. Baker, the designer of Burj Khalifa, did it in Broadgate in terms of he had to span the full width or the full length of the building over a railway station, and so he did it with an arch. So loads above are sitting on it, and loads below are sitting. So that's really the genesis for developing a concrete solution, which, when we originally did it, these extended out, these were continuous. But the more the M&E services got on board, the more that they had into these spaces, and it essentially became, instead of a continuous span, single span. But you can see the loads are coming down, and it's a story high funicular structure. So if you see that hanging upside down, it's this really, pyramidal shape. These are the 2 column loads coming down, and the reactions are taken by the ground floor plate. So it's really a story high funicular structure, no internal webs. Compression boom, and this is the tension boom. You can see this is trying to be pulled apart, and this, because these are inclined, this is pushing in. So really the beauty of that was to reduce the span from 18.4 metres in the basement to 12.5 at the upper levels. This was the parapet height that we had to honour in terms of planning, and as I said, the more the M&E got involved, the more we lost these spaces. But you can see essentially that the architect realised that the nature of these spaces at the upper levels needed corridors. They needed a designated circulation routes. So they were pushed to the sides, incorporate the M&E on top. So you've got architecture, M&E, structure up through the building. We kept with the steel beams in terms of, this level was set in terms of the street. This level was set because there was an existing slab really. You notice that there's a corbel here on this side that we had to introduce. Didn't really want to make a hole in that wall, but that was why actually, because we weren't mad about some of the stuff that we were seeing, so we said we'll engineer it in such a way that this is sitting proud of that wall. Okay? And any kind of interaction with this wall, we just wanted it concrete only. All of the horizontal forces are essentially taken out laterally through the floor plates. There's a bit missing here, as you can see, but there's gaps either side where that gets passed along. And you can see the groundwater levels here, the overburden of the rock. And that essentially, back of house was traditional flat slab. Constant steel beams at close space, 2.3 metre centres maybe. These beams are 1200 by a metre deep on a 4.6 metre grid typically. We widened out to just above 9 metres in terms of the atrium space, and just in situ concrete beams with 175 slab actually between. So between these concrete beams it's just a 175 in situ slab. The outside slab remained at 200. So that really, in terms of cost, in terms of benchmarking in the materials and the feel of a kind of a, I suppose, a library type building, an educational building, this kind of played into the architect's vision of expressing the the structure in the finished product. I just stuck this on before I came down because I've been on about M&E Distribution for the past 10 minutes, and this is one of Nervy's buildings, not too dissimilar in a way in terms of what's going on. The collection of the loads, and he's got a bit of small bit of bridging going on, although I'm not sure what he was at in some of it, but look at the M&E Distribution. 1950 style. Open the window and off you go. But I just thought it was a real driver in how the kind of the building was proportioned in this arrangement versus this kind of a thing, you know. Okay, so long span and situ concrete. One of the challenges is going to be deflection. So you'll see that the 3D model here, and we have the basement box, back of house all flat slab, ground floor with the steel console beams, and this is the transfer structure collecting all the upper levels. So essentially they were 12.5 metre span. The code deflection limit all in would be about 50 mil, which we weren't. Well, it's okay for span over 250, but it wasn't good enough for the 200 mil after construction. So we limited the deflections to 40 mil total from casting. But to be able to do that and tie in with the architectural finishes, we essentially had to pre-camber all of the in-situ concrete cores by about 20 to 25 mil. They were segmented, so at quarter points there was, it wasn't curved, they literally just had your 3 designated points on to match the curvature. So it was a segmented profile, and they essentially dropped by about 15 mil at about 3 months post decropping. By the time the screed came on board, they were essentially flat after pouring of the screed. So that was key to making sure that the total deflection long term would stay over 40 mil. And it worked pretty well on site. It certainly wasn't a nuisance to incorporate that. Just this is a slide in relation to some of the concrete finishes. It's probably best left laid on, but just to give you an idea of some of the kind of features that were happening. This is a back of house there actually, which sits on the transfer level of ground floor, and it's a kind of a cantilever stair off of the main spine core wall, all board mark concrete, and we ended up with this kind of dramatic stairs for starters, but a wall here. This wall is the height of the building from ground to roof, and maybe 14, 15 metres long, which gives you kind of a dramatic board mark effect. And in terms of the quality, the guys did really well in terms of achieving what the architect had in mind, and it's a good, I'd say, exemplar for board mark concrete if anybody's interested. Vibrations, I mean, one of the benefits of the concrete solution really was that it had better vibration performance in relation to how it reacts to footfall. So it was a win-win in terms of the performance requirements for the building, and all of the vibration requirements in terms of the client requirements were easily met. A few little details in terms of how we managed on the water ingress side, I suppose. This is at the base of the new build, where you have seepage piles, shotcrete, your wall and your slab. And I mentioned the cavity drainage, okay? So you can see there's drainage board here, which is directed down and directed under these walls at weak points, where we have the drainage board that passes underneath. And essentially all of the bottom base of the structure was a mixture of screed and insulation. So if anything did get through, we had a plan B, as to say. One thing we have to watch with there in terms of the intermediate floor levels, for a slab is coming in and wants to sever that. You bring your drainage board down, that's fine. What you've got to watch with that, I guess, is the detailing of how that interfaces with the soft of the slab. If you don't control it, we get a version of the traditional windowsill at home where there's a drip there for a reason. If you didn't have the drip, the water surface tension will keep in along the bottom of the sill. And the same would happen here if you didn't do that. So we just had a mixture of tubes that were inserted and below that line, so it couldn't go back up, which is an important detail in terms of managing the interface of floor plates. Of course, a big one then really was the metre thick slab, and we had the walls on both sides that had to make a cutting of, structurally connected together, waterproof it. So it would have been a saw cut, something you'd see in a James Bond movie. So a metre thick slab means 2 metre blade, and it's bigger than most of us. And thereafter we're hydro demolishing the slab edge back. You see this is a hydro demolished profile, so it's just water under very, very high pressure. The concrete will disintegrate, but the rebar will remain intact. And get a good clean as well for that matter. We refined that detail. Initially we had that as a kind of a lap length hydro demolition job, but it's slow. It's very messy. You know, you need several metres exclusion zone. It's dangerous. It's under high pressure. So we, in conjunction with the contractor, reduced the amount of hydro demolition that we have to do. Introduce couplers. So essentially, you're only cutting your slab, you know, within 200 to 300 mil of finished product. So get on your couplers. And that was the structural continuity re-engaged for the metre thick slab. The other thing you'll see here is the Irish waterproofing. So this is our re-injectable line. This is the first one. Your wet side you're going to do first, okay? And this is to be sure. This is your second line of defence, okay? We did that on walls and slabs. So that's a metre thick slab, and in fact the slab of all things performed very well in that regard. Quick one here on the strengthening. This I mentioned about the basement wall that we were asked to shift from one end of the building to the other, and how are we going to manage with this 350 mil thick wall? Well, I mentioned earlier about when you push these spaces down to the ground, you're going to need elaborate smoke extract systems for your fire strategy. That was needed for the two large spaces, being the sports hall and the auditorium. So they needed risers, and a big size riser in a part of the city where land is not easy to come by. So we managed, in conjunction with the architect, to nail the solution to this between architecture, M&E and structure by combining. If this was the existing 350 thick wall, we built an outside skin and then joined that to make a composite wall section like a ship's hull. And within the voids that would remain, we had smoke extract from two levels. So I suppose with the one kind of arrangement, we resolved the strengthening of the wall and where we were going to put these large risers on a very confined site. So both the team and the client were very happy with coming up with a combined solution like that. You can see here at these are the kind of fin walls that join the skin with the outer skin, and these are the large openings in those spaces to extract the smoke. Construction monitoring, I mean, we had everything you need in terms of you want to monitor, you want real-time monitoring, and that was the beauty of the data systems on this project, which it's becoming standard now. When this started maybe 4 years ago, it wasn't quite so standard, but it's certainly becoming the minimum that we should do on all projects. So we had the usual tilt meters, inclinometers, obviously the groundwater monitoring. We wanted to check the pulse of the site and the surrounding neighbourhood, and vibrations obviously on a continuous basis. And you need it. You will be called into action every now and then. There'll be rows about bits. Vibrations, and you can't beat having hard data to back up whatever discussion you need to have. Just into the piles, the construction pile layout. So We saw that in the original construction, the only seepage piles maybe the overburden, but certainly when we went to do the extension of the box, full depth piles was the order of the day. Not only did we do that, but in fact the contractor took it upon themselves to reduce the pile overlap as much as they could, to give them as dry a box as they could when we went down. So they took it upon themselves to reduce that, which was worthwhile. But you can see it's a mixture of 900mm piles where we're tight on the sides, and 1050 actually at the back, 1050 piles. But you can see, we spoke earlier about the shotcrete and how well a job they did in terms of treating the seepage piles, giving us a sound surface of the waterproof membrane. You can see the piling rig in its glory there. 2 piling rigs working from both sides until there was only enough space for one, trying to reduce the program. So just in short, it was female piles to 1/2 metre below formation, and then your male piles to 2 metres below. And the male piles are going to give you, in this case, your shear key horizontally. Then we're essentially into the props. Once you prop, you can dig, and once you prop, you can dig, and you can keep on that through the stages. One of the things we had to watch really in terms of the new seepage piles that were going in, they had to, there was obviously the existing anchors that were holding up this wall, which were still in use. Before we could take down this overburden, we needed to construct this outer seepage pile. We had to make sure we missed these anchors. So there was a lot of plotting and finger crossing to make sure that we missed the existing anchors, which you might see in some of the pictures. Just in the groundwater lowering, this is the groundwater profile up here, I suppose you can see, and the seepage pile goes in, but as we said, you're still going to get an element that are coming in under the seepage pile. But in terms of lowering what was in at this space predominantly, literally just started drilling through that space to be able to facilitate reducing the groundwater table within all of the water that was in this space. All of the groundwater, there was existing tanks that were utilised in terms of settlement and primary and secondary treatment. And the second line, it was done in 2 stages. So one kind of mid-height on the building in terms of drilling through, in terms of the overburden. And the second one was to intercept what might come up in terms of the rock. And that stayed there for the time being. So how do you manage all of this stuff that's coming through? Bearing in mind, this is full depth piling, but the original box was in partial depth piling. So it was going to come in, and particularly from the sides where we didn't have the full depth at the interface. So how that was managed on the ground was kind of a perimeter of land drains, okay, that would be collected. So it was done at the upper level, and the significance of this outline here is there's a level -5, in fact. You can see it dropping down to this level here. But essentially, we had a series of land drains that circumnavigated the box, including this lower basement level. All of the land drains were brought to this central sump point, so there was one sump point for the whole job. One point with two steel piles that were perforated with a granular sump in this area. And you can see these were the actual land drains that were brought to this at discrete locations. These had to be incorporated into the construction. So you can see as the building is constructed, we're constantly pumping out through these well points, and they have to be detailed. They're capped, and there's, in fact, I think the previous page had it there. These well points are permanent features in the base of the slab. They're cast into the slab, but they're capped and they're plugged, and and that's the final capping detail here. Just to give you an indication of the challenge and what the guys had to endure on site. This is the kind of water that's coming at them that they have to manage. Can you see this? Just take a look. So this guy here, he's trying to make his life easier by drilling some relieving points to get the water to be coming down at a lower level. And I will show you. Oop. Sorry about the construction noise. Just keep an eye on this here. So this is where the existing basement, the new basement met the existing basement. What you're seeing here is a miniature waterfall coming out. This is water that's pouring out here. So the drainage board was only used in this kind of -5 pits, so stuff that was coming through got directed down into these land drains, brought to this. And it's only when you look back actually at that footage, you see when it came to the blinding and setting of the waterproofing, it was as dry as a bone. In fact, like the job that they did in terms of managing what was coming at them. This is the land drain that's put in around here. So just to go back to that picture, brown's the kind of traditional drainage board that we see. So anything that was coming at those walls was directed down into the land drains, and we have our two steel pipes within a kind of a geotextile wrapped sump, which was the collection point. About 3 litres per second pumping out there in terms of the groundwater ingress. We've covered the client, the due diligence, the design, the challenges, the design, how the design responded to that, and I suppose the last piece of the pie was really for constructing the thing, and the interface of the existing box with the new box coincided with the atrium. That's the natural place to put your crane. So until we could demolish this back wall of the box, they needed a mobile. So to put that crane in there, they needed a bigger crane. So they managed to put an 80-ton mobile into the box, which essentially serviced as their tower crane for the early stages of the project. We're starting here, we're kind of working from left to right. You can see here the seating piles. These are the anchors that were holding that seating pile wall up. So it was the extension of these anchors that we had to negotiate when we were doing the new piling. And you can see essentially they will excavate the kind of waste level to let you put in the steel propping in the whalers and so on. Once you have a level propped and anchored, these are the first row of anchors that are actually going in here, and you can keep going. So you're still in the overburden there. A lot of demolition. I mean, I suppose in terms of the basement, in terms of the nuisance effect, let's say, of this construction, demolition and the brocks. You see the brocks here, the mini remote controlled machines. That jackhammering, that is the nuisance on a project site like that. Seeking piling, fine, no issues, even into the rock. But the demolition, especially in hard to get areas, with these areas they're munched. So the more munching you can do, the better in terms of reducing the risk on that. Again, as you're working from left to right, there's a row of cropping after going in. You can get a feeling now of the formation of this new box beside the old box. And you're beginning to go down, and each time you're adding the props that let you go down a level, and lets you go down a level, and lets you go down a level, until you get to the bottom. And I suppose that gives you a feeling of the kind of complex web of, these were existing props belonging to the previous regime. These were new props that were put in to make that 350mm wall stand up until it became a composite section with this skin. This is because we had to take all these intermediate floors that profited away that needed some help, as we say. So there was, as I said, it's only 40 metres to 30. It's a confined site. There's a hell of a lot going on. Not a huge amount to set down outside of it. So it really was a challenge for the guys to coordinate everything around all of these props. And these all had to stay until our floor plates started going back in. Okay. That's the footprint of the first board of water tanks. So that's the -5 level there. I think there's one other picture. So this is the this is the vantage point that the client had. So the client, that was their view. They could see us. So when we were doing BCAR inspections, we would wave to them. The digger. So the material was all extracted with the long reach excavator. So normally you see these in port dredging and the likes. So essentially, the material was all manhandled in a way into a heap here, and that was literally just taken out by excavator. A precarious job. They really were like dancers when they got in motion in terms of material moving from here to here to up. They did really well on that. So that's the bottom of the box, and we really then have to start coming back up through the building. Okay. So as each level is coming up, you're pouring your slab, you're waiting for a certain minimum strength, agreed with the temporary works designers. Your the anchors and the waders all clash with the wall that's going to come up, so they all have to be removed after this is strong enough to take the earth, the geotechnical loads. This just gives you a feeling of the auditorium. We spoke about the constant steel beams. 520, got a good load test today. All the dignitaries in the world were well on it, but I spoke earlier about the corbel on this side of the wall. This wall proved a bit problematic to us, as we, in fact, we knew it was a bit something to be wary of in terms of making holes in and how you might sit a steel beam into the wall. In any event, we did create pockets, again with hydro demolition, to make the reinforced concrete corbels on this side. It's predominantly concrete frame building, so on the far side we've got all these steel beams coming from 3 directions, in fact, that need to sit on these columns that go right up through the building. So this design actually evolved from being 3 separate plates, your traditional in plate of a steel beam onto a concrete column. That evolved into essentially a corset with right on the column. We got all 4 sides, and so that's how the steel structure interface between corbel, in situ corbel on one side and a steel support onto a concrete column on the other side. The steps was all in situ concrete pours. I suppose when we've done it in the past, they're typically precast maybe. Program issues drove that, and the guys had an ingenious method of creating that curve profile and propping with plastic tubing actually, which would give them the exact profile that they needed once set out. But it created a mightily impressive space here underneath, and on top for that matter. I mean, it's a big space to fill up. So we couldn't put the superstructure backpropping on those beams. Just wasn't going to take it. So we had to backprop those steel beams at 3rd points, and it's a mixture of steel beams, which we're doing other work for geotechnical reasons, and these hydraulic props. So all of these have to come back out through the lift, by the way. These extend down, and you get into sections that you could get them out through the lift. So you're getting your first glimpse there of the ground floor, and you're not going to see it here, but I have the viewpoint. You can see the pre-camber on the beams. So whilst the soffit was essentially faceted, the top profile of the rebar took a curved profile. So a big part of the transfer structure was these B columns and how they were going to become part of the architecture. And they were a bit of a pain because you can see here, there's a line here where it changes shape. There's another plane. So there was a couple of different planes going on. So much so that the only way you could wrap around it was to make it in 3 pieces. You couldn't do 2 pieces and take it apart. It had to be 3 pieces because the last piece of the jigsaw was a rebate up through the middle of the column here. But they, this is the prototype in terms of the reverse mould. So they'll make a full column in MDF. Then they'll make the fiberglass mould from the reverse mould. And that's what comes to site. We only had the one. Program wise, the building was to go up front of house and back of house together. We had some issues where the back of house had to accelerate, so it left them work around the idea that they really only had one mould to work with. So they would pour and move on and move on. But you can see the progression here in terms of, in fact, there's that rebate I spoke about. You know, we've got to get some bit of feature in there, but the quality is excellent. It's a 50% GGBS mix. The first pour, they didn't do a trial sample. It was, went straight for the kill, but we picked a column location which was less sensitive. There was a bit of kind of air pockets that would accumulate at the back face of this in terms of the air rising to the top of the mix. But in general, that was after the first one. They reduced this, they increased the slump a little bit thereafter, and everybody was pretty happy with the end result. So you can see here where the rain columns merge with this first floor's concrete beams to perform the transfer structure. Basement waterproofing, just to go back to the finished end product. So we have our slab, and in terms of that added level of protection, we have our drainage board, the insulation, and then your screen on top of it. So anything that does come up here, it's got a root. Okay, now there's 5 sumps in the footprint of the building. We can never tell if they're fully dry because they have to have them wet to test them, which they need to do twice a year. So, but we know that the pumps aren't working. So in terms of they don't pump water out. So the box is essentially dry, and this is your extra level of protection, your Type C protection. Okay. And I suppose it finishes with the end product, and we have at the bottom the multi-purpose sports hall, and I suppose really for them that doubles as an exam hall. So that's it's not just sports, but it's all the exam facilities that they get out of that. So that's at the bottom, and on top of that is the 520-seater auditorium, which had its full load test today. This is the corbel. I didn't even speak about the corbel at the front of the building, but the basement extends out into the street. You can imagine the tenement buildings would have had cellars at the front, so the property line at below ground extends out, but there's a defined street frontage line. So the basement wall was about 1.5 meters beyond the facade of the building. So if things weren't challenging enough, there was one last thing to kick us with. But and in fact, that was an in situ corbel for the full length of the building, and it looked so well that after the thing was done, the client thought it's a shame to cover it up. Can you imagine that? The client wishing that you didn't cover up a corbel, but that's really the finished product in terms of the clinical facilities up the upper levels, the atrium, and this is the entrance with the atrium, the second atrium, and I suppose we've been lucky enough to be awarded the building category of the year in 2017 in terms of the finished product. So that's it. There is a time-lapse video, if I can put it up in the machine here. It's about 2 minutes long, but it just gives you a feeling. So this is the 5-story building beside us. So York Street here, give your bearings, St. Stephen's Green off on this side. And let's dig and see what happens. But plenty of machinery. Robot boy. So they're already down the 4 stories there. You can see here the density of services. There is a shot of the servicing that is in some of the ceilings there. No hope. So that's back of house, and you can see the auditorium under construction here. So this is the back of house now, coming up. The back of house, for reasons I won't go into, programme-wise fell behind and it had to go up as a separate building almost. It's up in the clinical suites.
Well, Eddie, what can I say? Absolutely, thank you very much. I think
And thanks for the opportunity as well.
Yeah,
well done, Nuala.
Here, that's really entertaining. As far as I'm concerned, I'd rather pretty much that any day. I don't think that's the first award that you're going to be winning either for.
It's actually up on Friday for anybody that is into buildings. The architectural awards are on Friday, and there is part of it which is one category which is a public choice award. So feel free to contribute.
Right, I'd just like one comment involved in CM exam prep course on behalf of the regional group here this year, and part of a feature of the CM exam we nearly said this is the client possibly free.
Yeah, it's got that written.
Environmental conditions, and actually you've had that's maybe like a
yeah, it is, and it is like that, and you do wonder when you do those questions, who in their right mind would, stick a sports hall, 16 metres below ground. The engineering solution is to put a hoop out in Prouds Lane, as I used to say, but it's just the particulars of that client and what they needed. These things can happen, so you got to be prepared for it when it does.
Just want to open that. Any questions from the audience? I have a few. Shoot it. Yeah. No.
The carving. Let's go back to the cross section. So directly on that structure frame, so you probably got about 15,000 kilograms or something like that, depending on the building page. That carving is sitting in an existing 350 wall. See that one on the left?
This one here, is it?
Yeah.
Or this one?
On the next one.
The big one?
Yeah.
Yeah. Well, so the top of that wall essentially hadn't been poured, and
The lower section is 350, was there, or 500?
it was supposed to be 500.
So all that load is coming in into a moment.
You can see that the top of that wall hasn't been poured. So we had that wall only made its way to whatever 3 or 4 meters below ground, and what was behind it was sinking piles. So we had the opportunity to engineer what we needed to engineer for that top portion of the wall.
So basically, just never rewriting it just to get that moment.
Correct, yeah. But the moment is mostly taken off by the axial in terms of the twisting on that. Most of that is taken off by the axial forces on the slab.
just sitting there, it's just resting on its own.
Yeah,
There's no
yeah.
monitoring.
Well, it's more, that was the thing, I mean, we looked at, in fact, one of the things we looked at in terms of, if I go back to, I mean, it initially shouts, I want to be post-tensioned in terms of the, sorry, where have I put the, it wants to be post-tensioned because of the tension forces around this bottom boom. And in fact, you know, in terms of, this is a longer span compared to these ones, and, you know, once we had identified the idea of this transfer structure where all of these need to work in unison and it needed to be a monolithic structure, that's where we went with, kept developing on the concrete solution. So this is poured separately, so that is physically poured, but this is all monolithically connected into this field in terms of the reinforcement continuity. So there's full continuity in that whole arrangement.
There's more after going to wall.
There's a bit of moment in the wall, but most because it's all a tied piece, there's actually a force put into the beams as well. Think of the best way generally of thinking about that is think of the top of that wall and the corbel in an exaggerated fashion. So distort the deflections that take place. So for this to rotate, this needs to move. So if you pick a center of rotation anywhere, rotate it, and you can see that this point has to go right to rotate. You'll engage axial forces in the slab and the beam.
So that's such a stiff diagram.
Yeah, correct. And we did that for the full length of the building as well, so it's actually tied in to two end walls. I thought I had a better picture, just to give you, do I not have a...
Actually, just on while you have that section there,
Yeah.
we camber the slab, so you have your vertical
Yeah.
deformation, how about your lateral deformation, do you affect on those, and also your sway,
In terms of what it means for columns, is it?
Yeah, and
No.
the slab edges are...
On slab edges, we had, like what you're not seeing here is a grid of columns at the front here, which is literally 3 by 3 columns nominally, just to do your cladding at the front. So there's no pre-cambering here. So the pre-cambering is literally from here to here. But it kind of starts in terms of setting up from back here, but essentially this is the profile here. That's pre-cambered. These on the pre-cambered on so into the page, is it?
Yeah, I'm talking about like the outside as the camera settles out.
Yeah, we've no real issues on that. No real issues on that.
Any more questions?
Any issue when you look at that with growing the groundwater that you property?
No, I suppose the property to we didn't, and if I can just go back to the one that demonstrates it. I mean, one of the I suppose this one probably shows it best. You can see this building here that was piled all the way down to 8 meters into rock. This building, I don't think it's piled, but we're not entirely sure. And one of the things about it is that you put in your seat piles, you're expecting that to manage the groundwater outside of your construction footprint to be kind of similar, but it did drop. There's no doubt about that. Dropped a couple of meters, but no impact on surrounding property. Yeah, correct. Yeah, I mean, there was obviously a full delapse of condition surveys of existing buildings and all that kind of stuff. But I think what helped really there was that depth, in terms of most of the surrounding properties will have basements. Okay, so the starting point is that they're filled, and the depth of fill that's in the neighbourhood is essentially a basement deep. By the time you get to the bottom of that, you've got medium to dense gravels. It's not long before you're into good gravels, and then your rock is not a million miles away. So that's the depth of your gravels. So between the gravels and the fact that the rock isn't that far away, helped in terms of groundwater lowered, but yeah, yeah, and I suppose for me anyway, the interesting thing about that was how long it took for it to go back up. So it took months. It took months for the groundwater on certain walls to get back to where it would have been before we started. But there was a continuous monitoring regime between movement and delapse, and we were quite.
Just at a comment there on that in terms of what there's that curiosity moment. You might maybe just add.
Yeah. I will, I suppose. We've got to do what every engineer wanted to do with a box like that. Puncture a hole in it. In the early days, when we did all of the material testing, we kind of debated that and said we don't want to puncture this box because we don't have a team on site that would manage all of the gubbins that would fall in from that. But the temporary works that were there, that would have had a design life of 2 years. Okay, so when the contractor was coming on site, one of the due diligence exercises was, and in fact it was a client need, so they had a site that had temporary works which had expired. So one of the early things was to re-establish the appropriateness of the temporary works that are still there. Is it safe? Do we have to hoard the street off? And then you can, this is one of the early things as well, but we don't want these things coming out here. But that went down. There was some minor works, in fact, to do to temporary works, but not a whole lot. But we're on site and they had spotted an issue, and part of that issue needed to, one of the ways of resolving that issue was to lower the groundwater table. So in relation to temporary works, so it was this elevation here. So we had 3 holes, somewhere around 60, 70 mil hole, or there may be 100 mil. I don't even know if there were 100 mil, but there was 3 holes drilled in this wall, and I call them the Goldilocks of water, because one came out full bore, one came out half bore, and one was dry. So I suppose the lesson learned to that is when you are doing investigations, you have to you really have to do a couple of them to know what's going on. And I personally would have thought if that was a box that was surrounded with groundwater and you punctured through it, I would have anticipated kind of a jet that would dissipate, like the classic kind of jet of water that just runs out of steam. But no, it kept coming and it kept coming, and it was full bore and it kept coming, and it showed absolutely no signs of dissipating in terms of the energy that, I mean, it wasn't, I wasn't there for the very beginning of the jet coming out, but I was on site to see the general flow that was coming out, and it essentially filled the box with 300 or 400 mil of water before we had to say we got to stop, because we're not going to be able to reduce it within a short space of time. But it was an eye opener in terms of, I suppose, expect the unexpected in terms of ground conditions.